Solubility refers to how much of something can dissolve in a certain volume of solvent, which is usually water in our case. Solubility refers to an amount, often presented in grams, that is dissolved in a certain volume of solvent, often in milliliters. And this is the maximum amount of a material that can be dissolved in that solvent. Once you've added more than that amount, the solid will start to precipitate, which means it'll just stay together as a solid and clump together on the bottom of the container. And precipitation reactions are reactions where the products of that reaction have a really low solubility, and then they precipitate, or they settle as a solid on the bottom of the container. And there are no really good strict rules to decide whether or not something is soluble or if it will precipitate, at least not based on things like easy physical properties like charge or size or things like that. So generally you have to determine solubilities based on experiments, but at least for the common ions, there are some general guidelines that we can follow, and we've got them tabulated in a chart on this example. So this chart lets you do a good prediction for whether or not a given ionic compound will dissolve and split into its ions, or if it will precipitate. So lots of things can dissolve, molecular or ionic. If you have something molecular like a sugar, it can dissolve. You can take solid sugar and dump it into water, and the sugar will dissolve into solution just like it does in your coffee. And ionic things like sodium hydroxide, if you take solid sodium hydroxide and dump it into water, it'll dissolve, but while it does that, it will also dissociate. So it will split up into its ions because sodium hydroxide is a strong electrolyte. So what we'll do is we'll look at a couple of different examples with predicting solubilities. So the first set of examples will be based around the question, is it soluble? And we have 4 examples here of ionic compounds, and we're going to use the chart to decide whether or not these things are soluble. And the way we use the chart is we look for the anion, which typically is the ion written on the right-hand side of that formula. So for example number 1, we have Fe2+ and NO3- ions making up that iron 2 nitrate. So we look at the anion, the nitrate ion, and we see that nitrate ions are on the top of that chart under the section labeled soluble compounds. So NO3- compounds, things that contain the nitrate ion, are always soluble, and if you look at the very right-hand side column, you see important exceptions, and there are no exceptions. Any compound with a nitrate ion is always soluble, so we can say that iron 2 nitrate is soluble. Our second example is Cr2S3. This is a chromium sulfide. So again, we split this up into its ions, at least to decide what the ions are. This is made from a chromium 3+ ion and an S2- ion, actually 2 chromium ions and 3 sulfide ions. We look at the chart and we find the S2- ion. It's in the bottom under the section labeled insoluble compounds. So in general, anything with a sulfide ion is insoluble, which means it will precipitate. We look at the right-hand column for important exceptions, and we see that any sulfide ion mixed with ammonium or alkali metal cations, calcium ions, strontium ions, and barium ions, those are exceptions. Those would be soluble. Chromium is not one of the exceptions, so this is insoluble. Our third example is potassium phosphate. So again, we split into ions, and we check to see whether or not the anion predicts whether or not this thing is soluble or insoluble. We have potassium ions, and we have phosphate ions. We look for the phosphate ion. The phosphate ion shows up on the bottom of the chart under the section labeled insoluble compounds. And that means anything with a phosphate ion is insoluble. Then we check our exceptions, and we see that compounds with ammonium or alkali metal cations are the exception to that rule. And we have potassium ions. Potassium ions are alkali metal ions, so they're an exception. So this one is soluble. Our fourth example is PbCl2, lead chloride. We split it up into ions. We have lead 2+ ions and Cl- ions, the chloride ions. So we look for our anion. We find that chloride ions are on the top part of the chart under soluble compounds, and that means they are always soluble, and the exceptions are silver, mercury, and lead ions. Mercury is one of the exceptions, so this one is insoluble. Our second set of examples is based around the question, is the product or are the products soluble? And this is very much the same type of question that was given in the first example. Is the compound soluble? Here what we have to do is slightly different though. We have to decide whether or not a reaction happens at all, and if a reaction happens, if the products are soluble. Generally, with ionic compounds, they undergo what are called metathesis reactions. These are also called double displacement reactions. So you look at the ions and you swap them effectively. So the cation of the example on the left, HCl, goes with the anion on the NaOH and vice versa. So what you can do is you can say the H goes with the OH and the Na goes with the Cl. They just switch dancing partners. So we write a little reaction arrow and we say that we make H2O or HOH and we make NaCl. And then we can use our chart to decide whether or not these things are soluble. Water obviously is soluble in itself, so we don't have to worry about it. Then we look at NaCl and we decide whether or not that's soluble. We know from practical experience that it has to be, but we can use our chart to work it out. The anion is Cl-, so we look at the chart and we see that Cl- ions are almost always soluble. When we look at our exceptions, sodium is not one of the exceptions, so it's definitely soluble. So the NaCl is soluble. The next example is sodium carbonate reacting with barium acetate, and we do the exact same thing. We say we have two ionic compounds, they're undergoing a metathesis reaction, so they switch their dancing partners. The sodium goes with the acetate, and the barium goes with the carbonate. So we write our reaction arrow, and we've made sodium acetate, NaCH3COO, and we've made barium carbonate, BaCO3. This isn't balanced. On the left-hand side, we had two sodiums and two acetates, so we write a 2 here to balance our equation. And now we have to decide whether or not either of these two products or both of them are soluble or will precipitate. So we look at the sodium acetate first. The acetate ion is our anion, and we look at our chart and we don't see it, or rather we see something that is similar. You can also write the acetate ion as C2H3O2-, along with our sodium plus ion. And C2H3O2- is present in our chart. That's the acetate ion, just one more way to write it. And it looks like acetate compounds are always soluble with no exceptions, so we know that the sodium acetate is soluble. Then we look at our barium carbonate, composed of barium 2+ ions and carbonate 2- ions. We look for carbonate 2-, our anion, and we see that it shows up in the bottom under insoluble compounds. So carbonate salts, carbonate compounds are always insoluble, they always precipitate, and the exception is ammonium ions and alkali metal ions. Barium is neither, so this is insoluble.